So we've made it to our lesson on acceleration, and as always, we'll start with the passage. The motion of any object can be described in terms of displacement, velocity, and acceleration. So it's a good place to start, and then we should ask ourselves, where is this relevant to living systems? So let's give a few quick ones. We have motion, and this is kind of any time you're changing your speed. So you could have motion from rest or kind of from one speed to another speed. You can talk about growth rates. You can talk about nutrition transport or delivery, and this is also relevant to kind of your rate of absorption or your rate of nutrition. Kind of transport can vary depending on homeostasis or on your environment. There'll be times where you're going to need kind of faster blood flow or slower blood flow. And then this is kind of straight out of a Khan Academy passage. You can even talk about kind of more silly topics like the acceleration of an elevator. So let's do our introduction to acceleration. Acceleration is the change in velocity for some unit time. Let's start with kind of a quick overview of motion in general. So we have kind of three big topics. The first one is displacement or position. The second one is velocity. And finally, we have our new topic, acceleration. So the change in position, which is displacement, gives you velocity. The change in velocity gives you acceleration. And with these kind of three fields, we cover most of the motion that you need to know for the MCAT. And this could be a property of a living system, or kind of how things move in and out of a living system. So these are your big three: displacement, velocity, and acceleration. So it's a good way. We can also look at it kind of in the other direction. So let's go kind of way in the beginning. You can have an object at rest. I'm going to make a little kind of red ball. Could be a red blood cell. And then I'm going to apply some force. And this is going to be Newton's second law. We haven't covered it yet. But when you apply some force, you get an acceleration. So I'm going to go ahead and draw in this blue force. Anytime I have an acceleration, I have a change in velocity. We just mentioned that. So if I have an acceleration, and assuming I overcome friction, I have to assume that I have a velocity. So that's great. Because I had an acceleration, I have a velocity. So I'm going to go ahead and kind of draw in my acceleration, and that leads to a velocity. And kind of going up one more level, anytime I have a velocity, I have a change in position. So we kind of started at force, and we ended at a position change. So kind of just a brief overview of all of motion. So it's great to have a conceptual definition of acceleration in your head, but eventually we are going to need to calculate some things. So let's start with this kind of definition of acceleration. Acceleration equals delta v over time, so kind of the change in velocity and the amount of time it took to make that change. There's two flavors, just like velocity. The first flavor is average acceleration, and for this you need to define a trip. You define kind of the ending velocity, the beginning velocity, the end of the trip for time considerations, and the beginning of the trip, and you kind of just do delta v over delta t. On the other hand, you have instant acceleration, and for this again, we're going to have to take the limit as delta t goes to 0. So if you wanted the acceleration at time equals 5, you kind of have to hone in on time equals 5. You can do from 4.9 to 5.1, and then from 4.99 to 5.001, and eventually you get the slope of the v versus t graph at time equals 5. You just get the derivative. Let's look at our second formula, which should look familiar to most of us. And we have that velocity equals your initial velocity plus your acceleration and the amount of time between your initial velocity and kind of the velocity you're looking for. So this is kind of a very powerful formula. A lot of kind of MCAT students forget it, so I'm going to go ahead and write that down. And the nice thing about this formula is it doesn't use displacement at all. It just kind of gets you any velocity from any initial velocity, and you need to know how many seconds was it accelerating for. This is very similar to kind of the y equals mx plus b formula for lines. Oh, I wrote that incorrectly. Let me make a quick fix. Y equals b plus mx. So you can kind of see that a is the slope. That's kind of your m. Let's look at a quick example of how we can use this formula to get an answer. Some students might kind of mistakenly use the vf squared equals vi squared formula that we're going to cover in the next slide. But let's look at this. So we have blood flow is typically 0.3 meters per second During exercise, the blood velocity accelerates at 0.2 meters per second squared. What is the velocity of blood at time equals 1, 1.5, and 2 seconds? So nowhere in this question does it mention displacement or distance. It's not asking me to solve for displacement or distance, so I know it's a good application of this second formula. So if I kind of plug in 0.3 for VI and kind of 0.2 meters per second squared for acceleration, I get that at time equals 1, I'm going 0.5 meters per second. Time equals 1.5, 0.6, and then 0.7 for time equals 2. So exactly as you would expect, kind of for every second that I'm accelerating, gain 0.2 meters per second. So a simple enough application of a simple formula. Don't get kind of tricked into using a more complicated formula to solve such a simple problem. So we've kind of avoided the elephant in the room for too long. There are going to be times where you want to find displacement. So there's two main formulas that help us do this. The first one is Vf squared equals Vi squared plus 2AD. Vf is kind of your final velocity, Vi is your initial velocity. The nice thing about this formula is it doesn't use time. So if time isn't given to you and you're not looking for time, this is usually a good choice. It uses start and final velocity, so if those things you already have, then you're usually in good shape, or if you're trying to solve for one of them and you have all the others. And then lastly, you only need to kind of give directions to acceleration and displacement. Because Vf and Vi are both being squared, whether it's positive or negative, it's going to cancel out, and you're going to get a positive square, but make sure acceleration and displacement have a consistent sign convention. The second formula is displacement equals 1/2 AT squared plus VIT. And this one kind of touches all of your bases. It touches displacement, acceleration, time, initial velocity. You kind of use everything except for final velocity. You need to have directions for displacement, acceleration, and your initial velocity. Make sure you have a consistent sign convention. You could use kind of upwards to be positive. And the problem with this is if you're solving for time, you might get a quadratic formula, and you might have to say, well, negative b plus or minus the square root of something, who knows, no one remembers that. So you kind of get into kind of messy shape. You should still be able to do it, and sometimes the MCAT will have you estimate what the answer is. But if you do need to find time, there's two other choices, and they kind of cover them on the last slide. So you could have acceleration equals delta v over t, or velocity equals initial velocity plus at. These could kind of help you avoid the quadratic, but there will be times where you kind of embrace the quadratic and try to estimate an answer. The last thing for us to do is to have a good understanding of the velocity versus time graph. So I kind of made a random plot here. You can go ahead and remember that the slope is always your acceleration. So in this first piece, I have a positive acceleration, then a zero acceleration, and then a negative acceleration. And kind of at the end of this curve, it levels out. So I have almost a zero acceleration. So you could say that this curve has a decreasing negative acceleration, meaning it used to have kind of a steep negative acceleration, then a medium negative acceleration, and at the end, it's almost a zero acceleration. Now, if you want to talk about displacement, you can get that also from your v versus t graph, and your displacement is the area under the curve. So if I take the first piece and I kind of calculate that area, I would get that displacement. And for the second piece, I can get a displacement, even though acceleration is zero. And for this last kind of funky piece with this kind of complicated curve, I could also get my displacement by finding the area. So simple enough. Let's cover kind of a quick review. Acceleration is the slope of the v versus t, and displacement is the area underneath the curve. So you might say, why does the second piece have a displacement even though acceleration is zero? So you should kind of remind yourself, what happens when acceleration is zero? Well, if acceleration is zero, you have a constant velocity. Doesn't mean you have a zero velocity, it just means that the velocity is not changing. So if your velocity is changing, we call that coasting. You're coasting at the same speed. And it also means that your direction is not changing. You need an acceleration to change directions, because changing directions is changing velocity. Velocity is a vector quantity. So that's it for acceleration. Thanks for watching. Please like and subscribe for more lessons.